Simple bending. Welcome to the third video in the Simple Bending series. Dimensioning bent bars. Second example. Let's get started. We need to design the cross-section of the beam considering only the stresses resulting from bending. Assume allowable stresses for compression and tension. For compression, 160 megapascals. For tension, 120 megapascals. We also need to draw the distribution of normal stresses. We have a beam loaded with a continuous load and a concentrated moment on the left support. And we have a C-shaped cross-section. We are given dimensions 2a12a, between the sides 2a10a and 2a. For a change, I adopted a coordinate system. Receiving such a figure, either the axes of the coordinate systems are imposed, or we adopt them ourselves. For a change, I have now adopted one of the axes. We must take it as symmetry, as it will immediately be the central axis. Of course, we can accept it as any axis. Start the coordinate system somewhere here in the upper right corner. But anyway, the vertical axis will shift to this place because it is the axis of symmetry. So the symmetry axis is always the central axis, so here we have one axis, and the other axis is random, because it needs to be shifted to the center of gravity. And now I have also adopted a right-handed system, but the horizontal axis goes to the left, and the vertical axis goes down. In the previous video, the horizontal axis goes right, and the vertical axis goes down. That is also a right-handed system. Just like this one. It's important that the system is right-handed. You can draw the shear force and bending moment diagrams. It looks like this. So we have the maximum moment on the entire beam. This is precisely the moment from the parabola vertex, 11.74 kNm, and the strength condition. That is the maximum moment, the absolute value of the maximum moment, divided by the moment of inertia regarding the bending axis, that is the horizontal one, times. And here, if we take the distance to the tensile fibers, it's the tensile strength. The distance to the compressive fibers, the compressive strength. We have such a section, which is different from the previous example. There we had a rectangular section, and we immediately knew where the center of gravity is. Here we don't know where the center of gravity is. We have to find it, and move the horizontal axis to the center of gravity, to have the moment of inertia in the central horizontal. So we divide the figure into two parts. We divide it into a large rectangle, from which we cut, this will be figure 1, from which we cut this part, also a rectangle, and we will have the shaded area left. We could also divide it into 3 rectangles, for example. One rectangle here, the second one here, and the third one here. We would then do it as a sum, for example, of moments of inertia, or as a sum of the static moment of inertia as well. And we will make it as a difference. From the large blue figure, we subtract the green one. So we draw local coordinate systems at the centers of gravity of these figures, meaning in figure number 1, here is the center of gravity, at the height, where the height is 12a. Then, at the height of 6a is the center of gravity. And likewise here, simply halfway, like for a rectangle. Center of gravity of the green figure. So here we go. I won't go into too much detail here. In geometric characteristics, in the first video, everything is described what, how, and why. So the distance between the y-axis and the y-axis of the first figure, that's the distance along z, meaning z1 is 6a, half the height, z2 is 5a, half the height of the green rectangle. Area of the first figure 16, a times 12, a is 192a squared. Area of the second figure 12, a times 10a is 120a squared. And the coordinate zc is given by the equation z1 times a 1 minus z2 times a 2 over a 1 minus a 2. I note it down this way. You might also encounter the notation sx here, meaning actually in this case sy of the top over a, but it's the same. What I have here in the numerator is the static moment of inertia, with respect to the psi axis. I always write it down this way because it's easier for me, and here is simply the area of this shaded figure, and I substitute these values into the formula, the ones listed above. We get a result of 7.67a, and here we have the origin of the coordinate system at this point, meaning the positive z-coordinate is downward, and at 7.67a we have the neutral axis, which is the central I-axis. It is the neutral axis of bending, which means on this axis the normal stresses are 0. So 7.67a to the upper fibers, 4.33a from the calculation. Here 12 minus 7.67 gives us 4.33a to the lower fibers. And looking at the graph, we know that the lower fibers are in tension, so I've called this ZR this distance. And if the lower fibers are in tension, then automatically the upper fibers are in compression. So 7.67 is, I've called it ZC, the distance to the compressed fibers. And now the moment of inertia about this central axis, which we calculated, whose position we determined. In general terms, it's the moment of inertia of the first figure with respect to the horizontal axis, plus since this axis is offset from the central y-axis for which we calculate the moment of inertia, we have the application of Steiner's theorem, meaning we add the area of this figure and multiply by the distance between these axes squared, given as z1 minus zc squared. And we subtract the moment of inertia of the green rectangle, meaning this cutout, the moment of inertia of the figure at its center of gravity, plus the area of the figure and the distance to the axis for which we calculate the moment of inertia squared. Substituting all this into the formula, we get a result of 984a to the fourth. And now the strength condition, which is the moment for which we dimension 11.74 kNm, that is times 10 cubed, over the moment of inertia of the bending axis, meaning the horizontal one, 984a to the fourth. And now the first variant gives the distance to the lower fibers, meaning to the tensioned fibers, and here we insert the tensile strength, or the distance to the compressed fibers, meaning the upper ones and the compression strength. I check both conditions and choose the dimension such that both are met. Here, with the transformations, we simplify from a to 4, then we multiply by a to the power of 3, which remains, and divide by 120 times 10 to the power of 6, similarly here. From the first condition, a should be greater than or equal to the cube root of such, and from the second condition of such. Ultimately, from the first, it should be greater than or equal to 7.55 mm, and from the second, 8.30 mm. So, for both conditions to be met, we need to dimension to 8.3 and can assume that the area is equal. Since it should be greater than or equal to, let's assume 8.5 mm. Having dimensioned not the area but this dimension A, we can now calculate the distribution of normal stresses. That is the distribution of normal stresses in the most stressed section. So again, we have our section, it's known. Looking from the right side, that is the rule. We look from the right side in the place where we have the maximum moment. And this is a positive moment. Looking from the right side, counterclockwise moments are positive moments. So that will be the direction. And now, according to the right-hand rule, we need to decide whether the sign in our formula will be positive or negative. And as I say, here we can immediately, specifically in this case, generally in simple bending, we can immediately determine that the lower fibers are in tension. So normal stresses here at the bottom will be positive, and at the top will be negative. That is, on the tensile fiber side, normal stresses will be positive. But I want to show you a rule that will be useful later. So, following the right-hand rule, my moment is a situation on the right side. This is the moment, so I position my hand according to the moment marked on the axis. And since the y-axis is assumed in this example as part of the coordinate systems, that is in this direction, the thumb shows me that the y moment is consistent with the y-axis direction. So I can mark here on the section the y moment consistent with the y-axis direction. Therefore, the sign will be positive. The y moment of inertia, here I substitute, was 984 a to the power of 4. So for a, I substitute what we dimensioned to the power of 4. I get 5.14 x 10 to the minus 6 basic units, that is meters to the power of 4. And the stress function. And as I say here with the stress function, I do this, but it can just, since we already have the moment, we substitute the moment of inertia. And when you insert the coordinate ZC, that is 7.67, and this still has to be multiplied by AI, of course, you have the stresses at the top, which will be a negative coordinate. Since the origin of the coordinate systems is in this place, so here are positive coordinates, here are negative coordinates. The upper ones are compressed, so by substituting a negative coordinate, we get a negative result. At the top, the stresses are negative, and it's enough to calculate the value at the very top and at the very bottom, and connect it linearly, remembering that it must pass through 0 on the neutral axis. And we will create such a stress function. We divide 11.74 kNm by 5.14 m to the power of 4. We get 2284 x 10 to the 6 times z. And then it is in pascals per meter, because when we multiply it by z in meters, it gives us pa. And I will consider this 10 to the 6 as MPa. So then it looks like this. By substituting any value into any place of this section, I obtain the stress value at that point. And this 7.67 I will multiply by a here, which gives me 0.065 m. 4.33 I will multiply by a, which gives me 0.037 m. And I check at the top, meaning for the negative coordinate, I repeat. For the negative coordinate, I get minus 148.46 megapascals. And for the positive coordinate of the lower fibers, which are stretched, in this case 84.51. And as a reminder, normal stresses are 0 on the neutral axis. So here we connect passing through 0 on the neutral axis. And we have drawn it and done with the task. Thanks for your attention. In case of any questions, suggestions, feel free to write them under the video. Visit our Facebook profile, and we encourage you to like us on Facebook. Of course, also visit our website where you will find many tasks from various mechanics fields, material strength, structural mechanics. And don't forget to subscribe to us. Best regards, goodbye.